Today's lesson is about the existence, incidence, ruler, and plane separation postulates, and we'll cover sections 3.1 through 3.3 in our book. In this, we're going to go through a little bit of what we missed in section 2.5 and 2.6 in talking about what makes a proof and how to write one, as well as going through some of the basic ideas from the existence and incidence and all these other postulates, and then doing an example of a proof writing thing. If you've read through the sections, you might be able to skip through some of the definitions that we go through, but I decided to keep them into the video in order to make it more accessible for those who may not have read. So let's get started. To start here, we first want to talk about how do you write a good proof. Now, as we go through this, first thing we want to talk about is what is a proof, so that we know where to start. Now, we said before in class that a proof of a theorem, all these theorems are built out of conditional statements that connect these propositional functions, like we talked about the other day. So they're all of the form P of x implies Q of x, or if P then Q. So the proof of it is a step-by-step argument following the logical rules that we've talked about that justifies that statement. One important aspect of a proof is that every single statement in the argument must be justified by either an axiom, a definition, a theorem, or something previously shown in the proof. We can't use intuitive kind of ideas unless they're well defined. All right, so we need to make sure that everything we're doing, everything that we're saying, has a nice logical foundation so that it's easy to communicate to another person the ideas that we're trying to get at. So let's talk about several different types of proofs. The first one we want to talk about is the most simple one, and that's called a direct proof. A direct proof, as with all these other proof methods, are a method that proves a conditional statement of the form P of x implies Q of x. In a direct proof, this proof simply starts with the assumption P of x and leads directly to the conclusion Q of x. And you just basically connect the logical dots between those two statements. So it's simple to understand what a direct proof does, but sometimes this method actually can be a bit challenging. It may not always have a nice simple way to go from the hypothesis to the conclusion, and as such there are a few other types of proof methods that are available. The next type is the idea of the proof by contrapositive. Now, we discussed before that the contrapositive always has the exact same truth value as the original implication statement. So proving the contrapositive would also prove the statement P of x implies Q of x. So all this method actually does is to prove directly the contrapositive statement. The contrapositive of P of x implies Q of x is the negation of Q of x implies the negation of P of x. So in this case, we proved that statement directly. So we would assume not Q and show that that leads to not P. Now at first glance, you might think this might not be any better than a regular direct proof. The advantage is that sometimes it's easier to start with this implication, not Q, and lead to not P than it is the other way around. And so having both options available allows you to pick which one you think would be easier to do. The last type of proof method that I want to talk about is the idea of an indirect proof, or a proof by contradiction. This proof method is a little bit trickier to understand why it works, but still, it's a method that proves a conditional statement of the form P of x implies Q of x. However, in this case, instead of assuming just P of x, we assume P of x and the negation of the conclusion, and show that this leads to a statement that can never be true, which is something we call a contradiction. These can be things like both the statement R and not R are true at the same time. It can also be something that contradicts something that's well known, like for example, 1 is equal to 2. You run into something like that, then you know that both P of x and not Q of x can be true at the same time. What this essentially does is that it proves that the negation of P of x implies Q of x is false. or that no counterexample is possible. Remember that the negation of P of x implies Q of x is the statement that there is some value of the independent variables x such that both P of x and not Q of x are true at the same time. So what this method does is it assumes that you have such a situation and then shows that that situation is thus impossible. This shows that the negation of P of x implies Q of x is false, and hence the actual statement would have to be true because it has the opposite truth value. That's why the proof by contradiction works. So you're showing that there's no possible way to find a counterexample, so the statement must be true. One common pitfall with this method is that it's easily mistaken for a direct proof of the contrapositive. This is because both the proof by contradiction and the direct proof of the contrapositive both assume as part of the beginning of the proof that the negation of the conclusion, not Q of x, is true, and then follows along. So what will sometimes happen is someone will try to set up a proof by contradiction and claim that they assume both the hypothesis and the negation of the conclusion, so P of x and not Q of x. Then they'll follow a logical argument that actually only uses the fact that Q of x was false, so that not Q of x is true, and then leads to the statement that not P of x is true. They then claim that this is a contradiction to the original assumption that P of x was true, and hence has a contradiction argument. What's really happened, though, is that they showed that not Q of x implied not P of x, which is actually a direct proof of the contrapositive, and as such their proof should be reworked into that direct proof. The reason why it should be reworked into a direct proof is that a direct proof is always preferable to a proof by contradiction, because it's a little bit more clear and explains why we get somewhere. In fact, the hierarchy of proof writing is typically the order in which I gave them to you. If you can directly prove the statement, that's typically preferable to a direct proof of the contrapositive. And both of those are typically preferable to a proof by contradiction. Although sometimes proof by contradictions can be helpful, especially if you can't find a direct proof method, and so it's entirely a valid logical way of proving a statement. But kind of watch out for that. If you can find a direct proof, it's typically better. When it really comes down to proof writing can be thought of as a three-step process. We know we've got to use one of these methods, and so we kind of choose that. But when it really comes down to it, whatever method we choose, we have to figure out how to go from our starting assumptions to the conclusions that we want to have, whether that's assuming the hypothesis and showing the conclusion, or assuming the hypothesis and negation of the conclusion and showing some kind of contradiction. It always basically sets off with, here are my assumptions or my givens that I start with, and I want to get to the conclusions. So finding a path between those two is typically the most challenging part of the process. I think there's a three-step method that can help us do this, though. The first step in the method is to brainstorm. In this brainstorm period, you literally write down every piece of information that seems even remotely relevant to the situation. You can go through the book and you can find every theorem or definition that's related to the things that you're talking about in the question that you're trying to prove. You can find all sorts of things that way, sometimes things that you might not have realized. So you look for some keywords and you go through the entire book. Also, as part of the brainstorm, you typically write down the things that you already know. For example, like as soon as you figure out which proof method you want to do, you can write down the things that you're going to assume as part of your baseline. So if you're doing a direct proof, you would write down the things that you know about the hypothesis. And then you would look through, as you're looking through all these theorems, to see if that hypothesis satisfies one of the theorems, or if you can use a definition in a way that can reword the thing a little bit. You also want to write down in this brainstorm phase what your target is. So again, if you choose to do a direct proof, your target might be the actual conclusion. If you choose to do a proof by contradiction, your goal would be to find some kind of logical contradiction, which kind of leaves it a little bit ambiguous, but at least gives you an idea of what you're trying to do. Having this baseline and your goal there helps direct the proof writing process. As you go through the brainstorm, you're going to notice that there's a lot of things that are connecting. Some of the theorems might make sense together, and you'll start to see different ways that kind of congeal. So as you're going through it, you look for how can I get from the things that I know or the things I'm assuming to the thing I want at the end. If you finally come up with a way that you think will work, the next step is the following. And that's to outline your solution. This outline process is actually what you used to think of as the proofwriting process in general, and because this is the two-column proof that you remember from geometry before, where you write down the statements and the reasons. As with a lot of processes that you've probably learned in mathematics, you'll find that as you get good at this, you might not necessarily have to always write down the outline, but it definitely helps at the beginning. So we should always try to write down a two-column proof because it helps us organize our thought processes of what each statement's justification is, which helps us make sure that we guarantee that every statement we make in our proof is justified. Once we've written our outline and we know how the logical process works all the way through, we're now ready to write the narrative proof. This is a paragraph-style explanation of the logic that you outlined in your two-column proof before. You're going to keep these in good paragraphs, just like in an English class, where each paragraph has main ideas and supporting details and such things like that. As you go through, it should be a clear read for the reader to see what the logic is. An important aspect of this is anytime you're writing is to remember who your audience is. As I said before in class, I'll remind you here, your audience is supposed to be some arbitrary member of our classroom. So your proof should be clear enough that if you were to read it to any member of our classroom, they would be able to understand the logic going on in the proof. That's the level of clarity you want to get to. All right. This is probably a good place to take a break if you're having a hard time keeping track of all this stuff. We've been in here for about 12 minutes, and it'd be a good chance to maybe pause the video, get a snack, or something like that. All right. Now we're going to get into the meat or heart of what it is we wanted to talk about today, and that's the first four neutral geometry axioms. We're finally starting to move into the basic substance of the course and talk about the actual geometry that built Euclidean geometry. However, to start with, the reason why we're going to call this neutral geometry is we're going to make no assumption about parallelism. So we don't know which of those three parallel postulates, the hyperbolic, elliptic, and Euclidean parallel postulates, is true. And we're going to see how far we can go with just those without making that assumption. This is sort of in the spirit of what some of the people at Euclid's time wanted to do by trying to show that you could get the parallelism statement from the first four axioms. So we're going to kind of give that a shot and set up geometry without an assumption of parallelism and see how much of geometry we can actually get. As we go through these axioms, I want you to look at how similar some of them are to the incidence geometry axioms, because it turns out that these neutral geometries satisfy the incidence geometry axioms, so they'll be stuck in there somewhere. The first axiom is the existence postulate. This says that the collection of all the points forms a non-empty set, and that there's more than one point. The reason why we have this is, first, this allows us to actually start creating objects, and it also guarantees that we don't have this sort of simplistic geometry of having a single point and no lines. We don't want to have that situation because that's just not as interesting as the other ones. And just like we said before in class, when you're setting your axioms, you're trying to define what context you want to talk about. The context that we want to talk about does not include a single point and no line geometry. And so we exclude it by saying there's more than one point in the set. The next axiom is the incidence postulate. This is almost exactly axiom 2 from incidence geometry, or sorry, axiom 1 from incidence geometry. It says that every line is a set of points and that any time we have a distinct pair of points A and B, there's exactly one line L that A and B are both on. The cool thing about this incidence postulate is it does a couple of things. The incidence and existence postulates together imply the existence of a line, because we know that there's at least 2 points from the existence postulate, and the incidence postulate then says there's a line between them. Also note that this tells us what kind of object a line is. It says it's a set of points. As soon as it's a set of points, the word lie on is actually defined, because lie on is now an element of, which is actually the most common definition we used in incidence geometry, and so it shouldn't be too unfamiliar here. There's also a note here about the notation we used for the line determined by A and B. We need a definition here because the next axiom is going to use this statement, and it might not be as familiar to some of you. So it's going to talk about the idea of a one-to-one correspondence. A one-to-one correspondence is a function that takes a domain A into a domain B, but it has to satisfy two conditions. The first is that it's a one-to-one function. You probably remember the notion of one-to-one from calculus, but here we want to use sort of the more precise definition than things like the horizontal line test because we can't graph anything. So here, what one-to-one means is that anytime you have two values of the domain x and y that map to the same number or the same element of B, it must imply that those two domain elements were equal to begin with. That's one-to-oneness. The other condition is something called onto, which some of you may have never heard before, but if you've taken linear algebra, you should have. And this basically says that every element in the set B is hit by some element in the domain A. Okay, so that everything is hit and it's done in a very unique way. It's kind of the idea that if you had all the elements in A go on a date with the elements in B, everybody would have a single partner for the date, nobody would be left out. Something that didn't exactly happen in my high school, but you know, maybe that's why I liked the one-to-one correspondences when I got to math, but I digress. Now we're ready for the ruler postulate. The ruler postulate looks a little complicated, but it's actually not too bad. Essentially, it says two things. The first is that anytime you have a pair of points that aren't even necessarily distinct, there's some real number, which we'll call PQ, that's the distance from P to Q. So this says that we have some kind of notion of distance between points P and Q. In fact, the distance will be 0 if P and Q are the same. But that's the basic first idea from the ruler postulate, is that there's some notion of distance in our space. The second is that no matter what line you start with, there's a one-to-one correspondence between the points on that line and the elements of the real numbers, such that if P and Q are points on the line that correspond to the real numbers x and y, then you have this one condition that says that the distance from P to Q has to be the same as the distance in real numbers between x and y, which is represented by this absolute value of x minus y. So essentially, it says that not only is there a one-to-one correspondence between the points in L and the real numbers, but that this one-to-one correspondence preserves the notion of distance, so that our distance on the line actually matches up with exactly how far apart x and y are in terms of numbers. This is why it's called the ruler postulate, because it basically says that every single line can have a ruler attached to it so that you know exactly the distance from any 2 points on that line. So here's an example of how this one-to-one correspondence works. If I have the point P here, it's going to be corresponding to this guy x down here. Q will correspond to the y down here, and what it says is that the distance between x and y has to match the number that we assign to the distance between P and Q, so that how this relation works is that it preserves this notion of distance. Now, there's going to be a whole bunch of different functions that we can use for this, including ones that might map Q to this guy over here and P to this guy over here. And so direction kind of isn't really specified very well. And so we have to have some notion of being able to talk about direction, because the line itself doesn't have a left or a right. Now, if you remember from calculus, we used positives and negatives to try to identify direction before, and we actually can do something similar here. This theorem, the ruler placement postulate, says that in addition to being able to place a ruler on every line, this actually says that we can choose where we place it. So a ruler is going to basically be a real line that we match up to the line itself that we're talking about. So in particular, I can pick where the 0 should be and which side of the line should be positive. So what this says is that if I start with 2 points, no matter what 2 points I have, I can find a coordinate function that makes P the 0, so I line the ruler up with the 0, and then I flip the ruler accordingly so that the Q is in the positive side. This allows me to basically identify which direction I'm talking about by using, instead of left and right, by saying that P is going to be the center and Q is going to be on the positive side, wherever it is. And this allows us to basically do it no matter where, no matter what we want to do. So if we go back to our diagram, it basically says that wherever we map P to, we can call 0, and then wherever we map Q to, which will be in the real number part, the positive part of the real line, is also kind of what we'll identify as the positive side here. This allows us to talk about things that are on one side or the other of the point P on the line L. And we'll actually see how this works in the example that we do a little bit later. The next idea we need to talk about is the notion of a convex set, because we need this in order to understand the next axiom. A set of points is convex if any two points in the set when they're connected with a line segment, if that line segment that connects them stays completely in the set. It's a little bit easier to see than necessarily to read, so let's take a look here. The shape on the left is convex, while the shape on the right is not. The reason why is that if I pick 2 points here and another point here, let's draw that a little bit better. Okay, the line segment that connects these 2 points stays completely inside the set. I apologize for the squiggliness of the line. My pen isn't the best on the screen. But the idea is that no matter what 2 points I pick in the pentagon here, the line segment between those 2 points stays inside the set. However, on the shape on the right here, if I pick a point here and a point over here, let's make that a little bit clearer. Wow, I can't get that point to work. Then when I try to draw the line segment between them, you can see how it exits the set. So there's no way to force every line segment here to stay within the set, and so this shape right here is not convex because those line segments don't stay inside. That's the idea. Now we're ready to talk about the plane separation postulate. What it says is that every single line separates the plane into 2 non-empty sets, which we call half planes. Both of these sets, they don't intersect, and they have to satisfy the following 2 conditions. The first is that both of them are convex sets. So if I pick any 2 points in any one of the half planes, the line segment between those has to be completely contained. The second one says what happens if I pick a point in one half plane and the second point in the other. In that case, the line segment between them has to go through the line L. So basically what it says is that every line creates a border between the things that are on one side and the things that are on the other. So in this picture here, you can kind of see what I mean. This line has separated the plane into 2 separate half planes, both of which are convex sets, because if I pick any 2 points in one of the half planes, the line segment between them stays in the set. But it also has the property that if I pick a point here and a point here and I draw the line segment in between them, it has to cross through the line L. That's what this line is here, line L. So that's what the plane separation postulate does. What this does is it gives us a way of talking about things that are on one side of L and then the other, because we don't have, again, a notion of direction. We can't talk about things being up or down or left or right. We can only talk about how things are oriented with relation to other objects. So this gives us a way to talk about things related to a line itself there. We'll define things, again, in terms of how they relate. So if I pick, for example, a point here and a point here, these 2 points are said to be on the same side of L. But if I pick a point here and a point on in the other half plane, they're said to be on opposite sides of L. So the only way we can talk about which side of L they're on is its relative position to some other point. So that gives us a bit of a challenge. It makes it a little bit more challenging to describe things when we're trying to prove stuff, but it's the only way we can do it because we don't have a notion of direction here. One of the last definitions, which I point out only for its notability, not because we're really going to talk about it too much right now, is the idea of an angle. We can take two non-opposite rays that share the same endpoint and then have an angle that's denoted by one of those things there. It's interesting that it says they have to be non-opposite. This means that in our definition of angle, a straight angle of 180 degrees, say, is not allowed. That's not considered an angle. And in fact, we'll define the interior of the angle. You can read that in the next part of the definition after this one in the book. It defines the interior of the angle as being an intersection of two of the same side, two half planes from the plane separation postulate. It turns out that the interior always takes on the smaller angle between the two. So if I have, say, the following, if I have a ray here and a ray here, the interior will always be the smaller angle and not the larger one. This means essentially, and we'll actually show this in the next section when we talk about angles and the postulates defining those, that no angle in this geometry will be considered to be larger than 180 degrees. In fact, all of them will be strictly smaller than that. So we won't use any angle that's bigger than 180 degrees. So all of our angles will go from 0 to 180 degrees. And anyway, so that's kind of a little bit different than how you might have done it in trigonometry, but this turns out to be the best way to handle it when we're just talking about the shapes themselves. That way we don't have any ambiguity about which angle we're talking about, because it's always the smaller side when we have two rays. All right, there's a huge number of definitions that start out in these first three chapters. First three sections, because we're trying to get a handle on what we can talk about, on how to discuss all these different geometry ideas. Before you panic, realize that most of these are actually pretty intuitive, like the idea of length, or plane, or an external point is a point off a line. Parallel lines, collinear, non-collinear, mean the same thing that they meant in incidence geometry. We have a few other notions that are a little bit newer, like the notion of being between for points or between for rays. So you want to make sure you go through these and get familiar with these terms. You're not necessarily going to have to be able to regurgitate their definitions verbatim, but you should be able to tell me what any one of these mean if I were to say ask it on a test. I know it seems like a lot, but like I said, a lot of them are pretty intuitive in the way they're defined. Okay, we're about to move into the example. This is the last part of this lecture, and this also is another place that might be a good spot to stop and take a little break if you need to. We've been going for about 17 minutes since the last break, and this would give you an opportunity to sort of maybe get a snack again and sort of chill out. Of course, you know, if you're really that entertained, I suppose you could have a bowl of popcorn in front of you, but you know, I'm not sure if that's how you guys feel, but you know, the jokes are even worse when you're trying to talk to a computer rather than to actual people. But don't worry, I can imagine your non-laughing faces anyway. All right, so now we want to look at an example here. So we're going to try to prove something, and we're going to go through the proof steps that I mentioned before of brainstorming, outlining, and then actually writing the proof. Usually in class, we won't normally have time to do all of this because we're going to work on them together. So usually in class, I'm going to rotate days between outlining and then actually writing down a narrative. Today, though, we have the opportunity that I can talk without any interruption with discussions and stuff like that, and so I'll be able to go through just a little bit faster. That said, of course, remember you can pause this anytime something doesn't make sense and think about it for a bit. All right, so here's the thing we're going to prove. This is corollary 3.2.20 in the book, and it says the following. Let A and B be two distinct points. If f is a coordinate function for L such that f of A equals 0 and f of B is greater than 0, then the ray AB is the set of all points on L such that f of P is a non-negative number. Now this might kind of seem, if you think about it for a second, maybe draw a picture, okay? This is saying that if I have a line here and I pick a coordinate function where this point A has 0 and this point B maps to something positive, then the ray, which starts here and goes this way, consists of all the non-negative numbers. That's essentially all it's saying. The diagram almost shows that our intuition is completely right here. But we need to actually prove this from the pieces of information that we've built this on. In particular, this is a corollary to theorem 3.2.17, so we should hope that that theorem shows up along the way. So now I said the first thing to do when you're writing a proof is to brainstorm, and you write down all the different ideas that you have. I neglected to write down the givens that we had in this part here. So the givens are, we have a line, we have a point A, and we have a point B on it. The point A corresponds to the number 0, and the point B corresponds to something positive. Those are our givens. Our goal is to show that this ray here corresponds to all the non-negative numbers that our coordinate function that map to A to 0 and B to something positive. It's all the things that coordinate function maps to non-negative numbers. So now let's go ahead and look through the book. In fact, if you wanted to, this would be a good place to pause the video and try to see if you can find how many different things in the book are related to this idea, and just try to write them down and see if they're the same things that I write down. The first thing I noticed that's related to this is the definition of a ray. Since we have to try to show that the ray equals something, it'd be good to know what the word ray meant in the first place. And so I wrote down what the definition of a ray is. Of course, this brings up to the point of what the heck is that and what's the definition of that? Well, that's a line segment, so that's a line segment. And so the next thing I wrote down is the definition of a segment. We'll notice here too that both of these include this notation here. This notation is for betweenness of points. If you don't recognize that notation, you might want to pause the video and look that up too, because I didn't write down the definition of that. The next thing I wanted to see is also the ruler placement postulate. This allows me to find a coordinate function that has the properties I already had. Now this one seems related, but it'll end up not being really all that useful, but since they already hand us such a coordinate function, so we don't need to actually assert the existence of one. But nonetheless, it's related and could have easily ended up on any of your brainstorming lists. Theorem 3.2.17 turns out to be relevant because it takes this notation here and relates it to something about how the numbers that f corresponds to. Since both of these show up here in the definition of a ray and a segment, and we have a line that actually ends up doing this for P and Q, it'd be good to see how those two relate. So that's why theorem 3.2.17 sounds like it would be important here. This is also a positive thing because corollary 3.2.20 is a corollary of theorem 3.2.17, so it should have shown up anyway. That could have been another reason why you wrote it down. Another one that seems that it could be useful is corollary 3.2.18, which allows us to see that if we have this property here, then these guys have to be true. Now, in the proof that I'm going to write, you could have used corollary 3.2.18 to make a few points. I end up not, but that doesn't necessarily mean you couldn't. So sometimes there's more than one way to explain something, and that's okay. This is definitely, though, a relevant corollary to what we're doing in the sense that it's related to things like rays and line segments, and also how coordinate functions behave, as well as betweenness for points, all of which were related to what we were doing. The last little bit is actually something that's not in the book, and it's something that you need to know because this is a common notion in general in proving things. We're asked in this proof to show that two sets are equal, that the ray AB is equal to some set of all points P such that f of P is greater than or equal to 0. Well, it'd be good if we knew how to show that a set was equal. So what the typical way it is to show that the set is equal, there are other ways, but this is the most common way, is to actually show both of these statements here. This first one is that A is a subset of B. And it says that every element of A is also an element of B. Now that might mean that B has more elements, but certainly everything that's in A is contained in B. The other way around certainly is the same thing. It says that every element of B is in A, which means that all the elements of B are also in A. Well, if both of these conditions are true, that all the elements of A are in B and all the elements of B are in A, then clearly that means that they have to be the same set exactly. Because there's no way that B could be bigger if all the elements have to be in A, and there's no way that A could be bigger if all the elements of A are in B, and vice versa. So that's typically what we're going to do, and that's how we're going to prove this, is we're going to show both of the subset statements in order to prove set equality. All right, now hopefully at this point in looking at the brainstorm, you might be able to see a way of doing this. So if we want to show say that the ray AB is a subset of the points that F maps to non-negative numbers, what we'd want to do is start with something in here, which means that it's either in this set or this set here, okay? Oh, you know what? In fact, I actually left something off on that, but I'll point that out in a minute. Boy, that threw me off, and I don't want to record these last 2 minutes. So I'm gonna take a second just to point this out again. So we're gonna try to show subsets here. So we're gonna say that the set AB is a subset of the set of all points that F maps to non-negative numbers. So we'll take things that satisfy these conditions here in the set and see if we can use some of these theorems, like in particular use this guy here, to see if this helps us identify that F of whatever of the point that we found in here has to make something non-negative. That's kind of the idea of where we're going to go. So you can see that in the brainstorm. Now the thing I wanted to point out that I messed up here is the definition of a segment, if you caught it, is also supposed to have the set A, the element A and element B, which aren't actually between A and B. So we got to make sure that that's in there too. I don't make that mistake in the proof, but apparently I made that mistake in writing that here. All right, let's move on to the next idea, which is how to outline this proof. So we've got to go through all the different pieces. The first, of course, is just to write down what the hypothesis was, that we have 2 points A, B on a line, and that F of A is 0 and F of B is positive. Next, let's start with part 1, which is the first half of what we wanted to show, that the ray AB is a subset of all the points P on the line such that F of P is non-negative. That's what we want to show. So that's our goal here. So I'm not actually saying that this is actually true. Now this is a 2-column proof, just like you normally would see. And so remember, this side over here is going to end up being statements. Well, you can't really read that, can you? And this side over here are going to be the reasons why they're true. Okay, that's typically how we're going to write it. So on the left are statements, on the right are reasons. So now let's start out with where we want to go. So if we're going to try to show subset here, we're going to start with an arbitrary element here, something that we don't know the actual value of, but we just know it's in there, and show that it has to be also an element in there. So the first thing we do is we pick a point Q in the ray AB. Well, what does this mean? Well, by the definition of ray, that meant that Q is either in AB, it's either or between A and B, or B is between A and P. That's what it means to be an array. If you just follow through the definitions, you'll see that Q has to be an element of one of those 3 things. So what this does is it tells us that in order to cover all of our bases here, we have to actually handle 3 different cases: case 1, case 2, and case 3. Well, so let's start with case 1. Q is in AB. This means that either Q is A or Q is B, clearly because that's what it means to be an element of that set. Well, this is 2 cases then. Q is A and Q is B, and let's see what happens. If Q is A, then F of Q has to be equal to 0, and that's because F of A is equal to 0 and Q and A are the same point. On the other hand, if Q equals B, this tells us that F of Q has to be positive because that's what F of B is. F of B is positive. And so, and Q and B are the same thing. In both of those cases, you'll see that F of Q is greater than or equal to 0, which is kind of what we wanted in the first place, because we're trying to show that Q is an element of the set of all points P that are mapped to non-negative numbers. So this handles case 1 just fine. We can move on to the next case. Case 2 is that Q is an element of the points P such that P is between A and B. This is the next part of the ray. Well, if if Q is in this set, what it means is that Q satisfies this condition. So this is all the collection of P's. P is kind of a dummy variable here that stands in. So if Q is an element of all the P's here that satisfy this property, then it means that Q has to satisfy this property where the P is, which tells us that Q is between A and B. Well, theorem 3.2.17 says that if Q is between A and B, then either this is true or the other way around. Except that we already know that f of A has to be smaller than f of B, so there's no way for the inequalities to be going this way. So the inequalities have to go this way in greater in size, and that tells us where f of Q has to be. Well, that tells us then that f of Q has to be strictly greater than 0 because that's what f of A is. So that, of course, means that f of Q is greater than or equal to 0, which was kind of our goal in order to get it in that other set. Now we can do case 3. Case 3 is actually very similar. Again, we have Q is in this set here, which means that Q has this property for where the P is going to be. So B is between A and Q, which again, by theorem 2.17 tells us that this relationship has to be true, and it says that it's either that or this one, but we know this one doesn't work because f of A is less than f of B. This again tells us that f of Q is greater than 0 because f of Q is greater than f of A, which is equal to 0. Or if you want, f of Q is greater than f of B, which was also greater than 0. So we're basically using the transitive property of inequalities there. So in every case, f of Q is either greater than 0 or equal to it. This means, of course, that Q has to be an element here because it satisfies the condition for being an element of that set. Well, Q is an arbitrary element of the ray, and now that shows that every single element of the ray is an element of this set, which is exactly what this subset thing means. So we've actually proven now that the ray AB is a subset of that guy. So now we're ready to try to prove the other direction, and that's part 2. So now we need to start with an arbitrary element here and show that it has to be in the ray. This is actually a bit easier. So let's start with that. Let's pick an arbitrary element Q that's in there. Well, that tells us that f of Q has to be greater than or equal to 0 because that's the elementhood test there. If it's greater than or equal to 0, that gives us two possibilities. Either it equals 0 or it's strictly greater than, which actually leads us to two cases. The first case is f of Q is equal to 0, but f of A is also equal to 0. But remember, f was 1 to 1, which means that if you have f of A equals f of Q, then those domain elements had to be equal to begin with. So that tells us that A has to be Q. But A is an element of the ray AB, which means, of course, since Q equals it, Q is also an element of the ray AB. So in this case here, Q ends up landing on the ray AB, which is what was our goal for part 2. Case 2 is f of Q is greater than 0. This gives us two possibilities. Since we know that f of A is less than f of B, then that means that Q is either in between them or it's on this side over here. So that gives us these two possibilities here. So there's the two cases individually. The first one, of course, by theorem 3.2.17 says that this is true. But that's exactly one of the elementhood tests of one of the elements in the ray, and hence Q has to be in the ray AB. You can look up the definition of the ray to see this guy sitting in there as one of the elementhood tests. Similarly, in case 2, we get that Q is between A and B, which is also one of the elementhood tests for one of the things in AB, and that forces that Q is in the ray AB. So since Q is in AB in every one of those cases, and Q was arbitrarily an element of this guy, that shows that every element here has to be an element here, which is exactly what subset means. Finally, because we have both subset pieces, both this one and that one, that's what it means to be equal, and we have now proven equality. Now this is a 2-column proof. It was a little long because there was a lot of cases to show. So now what we need to do is translate this outline into a narrative proof. Okay, so I'm hoping you wrote down the outline so that you can actually see how this proof is going to go as we move along, because it's going to be sentence for sentence what we did in the outline. So here we go. We write the word proof and we're ready to go off running with our various statements. The first thing we write down is the hypothesis, exactly how it was written in the theorem. This gives us a nice place to set things up. Now, depending on what textbook you read, sometimes they won't actually write down the hypothesis, they'll just assume it. But when you're getting started with proof writing, it's always a good place to start by writing down the hypothesis that you're starting with. Now we're ready to show containment both ways. Remember, we want to show that the ray AB is equal to the set of all points P that F maps to non-negative numbers. And that our goal in doing that was to show that the ray AB is a subset of that set and vice versa. What we're going to do here is actually go ahead and do that proof. I haven't written down what the strategy is, but I will point out that it's not a bad idea to put an extra sentence here that actually describes your strategy that you're going to use. Sometimes it helps give a bigger picture view for your reader. So I could have put a paragraph in at that point in the arrow that said that to show that the ray AB is equal to the set of all points P such that f of P is greater than or equal to 0, I'll show containment both ways, that the ray AB is a subset of that set, and that that set is a subset of the ray AB. That sets the strategy, and then the reader will expect the next part to come next. But anyway, we'll start with Q is in AB and show that it's in the other set. Sorry, the other set. So here you can see we use the definition of ray to tell us the three cases we have. And then we move into each case. So again, we suppose that Q is in AB, then Q is in A or Q is in B, and then we handle the two cases, since they're short, in the paragraph itself. If Q is equal to A, then f of Q and f of A is equal to 0, and hence you get f of Q greater than or equal to 0. This is kind of nice to start to end with there, because that was the conclusion we need on this case. And you do the same thing for Q equals B. Notice these are all complete sentences, and it describes exactly the logic that we pointed out in our two-column proof. Now for case 2, we're going to suppose that Q is in this piece here, because that's the second part of the ray. Well, then that tells us that Q is between A and B, and then we can apply theorem 2.17 to do exactly what we pointed out in the outline. Finally, we point out that f of Q being greater than 0 tells us that f of Q is greater than or equal to 0, because that's the condition we wanted at the end. We can do case 3, and it's very similar. First, we point out where Q is, then we apply theorem 3.2.17, and then we point out that the fact that f of Q is greater than B, f of B, which is greater than 0, gives us again that conclusion. Now we point out that in every single case, we got that f of Q is greater than or equal to 0, and hence in all cases, Q is an element of the set we were interested in. Since Q is arbitrary in the ray, we see that the ray now has to be a subset. So that's the narrative part of proving the first part of the subset. To do the second part, we do the same thing in reverse. We start with something with Q saying that f of Q has to be greater than or equal to 0, and that yields the two cases f of Q is 0 or it's strictly greater than 0. And then we handle those individually. If f of Q is equal to 0, then f of Q has to be equal to f of A, and you can use the fact that f is a one-to-one correspondence to give you that Q is A, which means that Q has to be in the ray AB because A is. Next, you suppose that f of Q is greater than 0, and then because f of B is greater than 0, which equals f of A, you have, of course, either this or that situation. Both of those yield by theorem 3.2.17 that Q ends up on the ray in both cases, which tells us that in each case Q is in the ray AB. Since Q is arbitrary, we see that this has to be a subset this way. Finally, because we have both this subset and that subset, this gives us equality as required, and so we put our cool little box, or a QED, which stands in Latin for Quod et Demonstratum, which is Latin for I'm done. Which of course we are now. And there's a picture of Mickey Mouse happily having finished a proof in geometry, which I hope is exactly how all of you feel now. Anyway, I hope you enjoyed this presentation and that it helps explain some of this stuff. Please send me an email if you have any questions, and good luck with doing the homework. Hopefully you have enough to be able to handle the homework for Monday. Remember, there's no class on Monday, and we'll meet again on Wednesday.